Welcome to the Technology Primers module. In this module, we will cover the essential technology building blocks used in solutions for a connected home or small commercial space. This section is a primer on power theory. The intended audience is anyone without previous knowledge of electrical power who needs to understand basic technology and concepts. This includes several categories of personnel who interact with people that work with electricity, electronics, and electronic equipment. In this primer, you will learn what voltage and current are and the ways they relate to each other and to other electrical power terms and phenomena. You will also be introduced to the two different types of current and to two phenomena, capacitance and inductance, that are used to store and couple electrical energy. So let's get started. What is power theory? Power theory describes how components and phenomena interact in an electrical circuit. A complete definition involves answering what is for each of the terms involved in these interactions. Let's begin with voltage. Voltage is the pressure or electromotive force that causes electrons to flow in an electrical circuit. Its symbol in most electrical diagrams is the letter V. In physical terms, voltage is caused by a given electrical charge on a surface. More charge on the surface means more voltage. Differences in voltage mean there is a difference in the amount of electrical charge on surfaces at different points in a circuit. This difference is called electrical potential. In the physical world, all things seek to be at equilibrium, a state at which everything is balanced. Any difference in charge levels therefore causes charged particles to flow between areas of potential difference to balance charge levels. A couple of analogies may make this clear. A ball moves from a state of higher potential energy to lower potential energy as it drops to the ground when released from a height. Water in a tower will flow to a tap in a house at a lower point than the tower. The volt is the unit of measurement of electrical potential. Hence the name voltage and the use of the letter V to denote voltage. In an electrical circuit, current is the flow of negatively charged particles called electrons. Electrons flow in the direction of a positive potential, that is, from lower to higher voltage. Although at first this might seem like water flowing uphill, it can be explained by the fact that electrons are negatively charged. Physicists historically define current flow direction in terms of positive particles that flow in the opposite direction. In other phenomenon where positive particles are moving, current flow matches the water flow analogy perfectly. Current flow is measured in amperes, usually called amps for short. By definition, an ampere is a net charge of 1 coulomb passing through a chosen surface in 1 second. Smaller units are the milliampere, which is 1/1000th of an ampere, and the microampere, which is 1/1,000,000th of an ampere. The symbol for current in electrical circuit calculations is I. Alternating current is current which changes direction of flow on a periodic basis. The most common form of alternating current is a sine wave. However, there are other forms of alternating current, such as square waves, which have both positive and negative values. Frequency, amplitude, and phase are properties of periodic alternating current. Frequency is a measure of how often a waveform repeats itself. Amplitude is the instantaneous value of the waveform, and phase is an indication of the point where the waveform begins its first change from a zero value relative to a defined timescale. The changing magnetic field created by alternating current flow in a conductor is useful in applications requiring coupling of electrical energy without a hardwired connection. This ability is due to the effects of inductance, which we will discuss later. Power is the rate of energy transfer from a source to a load. Electrical power is measured in watts and is calculated by multiplying voltage by current, that is, V times I. This formula makes sense when you think about the physical definitions of voltage, current, and power. A voltage potential represents a collection of charges, and current flow is the movement of charges. The number of charges moved per unit of time is the rate of energy transfer. It depends upon how many charges are at the source and how fast they move through the circuit to the load. In a light bulb, light and heat energy are two forms of energy transfer that enable us to see the difference in power levels. A 100-watt bulb is brighter and emits more heat than a 40-watt bulb. By definition, the resistance of a device across which there is a potential difference V and through which there is a current flow I is V divided by I. This relationship holds true for any value of V or I. The symbol for resistance is a set of peaks and valleys that resemble sawteeth. The German physicist George Ohm found that for any given material, resistance is a constant, which means that any change in voltage must be proportionately matched by a change in current. In Ohm's honor, this constant relationship between voltage and current is called Ohm's law. Capacitance is a qualitative measure of the ability of a set of conductor surfaces to store electrical energy potential. A capacitor consists of a set of two separate and oppositely charged conductors. When we talked about voltage, we learned that an electrical potential exists between two charged surfaces. This includes the set of two oppositely charged conductors. Capacitance is defined as the charge magnitude measured in coulombs on either of the two surfaces per unit potential difference between the surfaces measured in volts. 1 coulomb per volt is known as a farad and could only be realized by an extremely large surface area. Practical units of measurement for capacitance are microfarads, which is 1/millionth of a farad, and picofarads, which is 1/billionth of a farad. A practical capacitor is small, has its oppositely charged surfaces easily insulated from each other by a material called a dielectric, and is arranged so that external electrical and magnetic fields will not disturb the distribution of charge on the surfaces. These requirements are met by capacitors with parallel plates or with coaxial cylindrical conductors. Similar to resistance, capacitance is a constant, which means that any change in charge must be proportionately matched by a change in voltage. The symbol for a capacitor in an electrical diagram is a stylized drawing of two parallel surfaces. Inductance is the property of an electrical conductor where a change in the electric current through that conductor induces an electromotive force, EMF, that opposes the change in current. When only a single conductor is involved, this phenomena is technically called self-inductance. The induced EMF is due to the change in the magnetic field surrounding the conductor that occurs as the amount of current flowing changes. Any device, such as a coil that shows the effect of self-inductance, is called an inductor. The effect of inductance is increased when the conductor is wound into the shape of a coil or solenoid by the square of the number of turns in the coil. This is probably the reason that in electrical circuit diagrams the symbol for an inductor is a coil. Inductance is measured in units called henries, which represents volts per ampere per second. Smaller values typically found in practical inductors are 1/1000th of a henry, called a millihenry, and 1/1,000,000th of a henry, called a microhenry. Electromagnetic interference, or EMI, is the introduction and propagation of unwanted signals in an electronic media via undesired radiated electromagnetic fields. There are several types and sources of EMI, but all have the same effect of degrading the quality of a good signal that occupies the same frequency spectrum as the unwanted signal. Capacitive coupling occurs when two closely spaced conductors act like the surfaces of a capacitor. Increases in charge on one conductor will cause a corresponding increase in the opposite polarity charge on the other conductor. Inductive coupling is caused by a phenomenon similar to those behind self-inductance. It is the result of magnetic fields generated by current flow in one conductor, causing a magnetic field that induces current in another conductor. Radio frequency interference occurs when conductors act like antennas to receive radiated electromagnetic fields. To sum up, we've covered the definitions of voltage, current, resistance, and electrical power, how Ohm's law describes the unchanging value of resistance over ranges of voltage and current, and the physics behind capacitance and inductance. Finally, we've covered how alternating current is different from direct current and defined electromagnetic interference, or EMI. This section is a primer on radio frequency, also known as RF theory. The intended audience is a person who has some basic knowledge of cable terminology and radio frequency signals. This may include several categories of personnel who interact with people that work with electricity, electronics, and electronic equipment. In this primer, you'll learn how RF waveforms relate to the most basic waveform in nature, the sine wave. We'll show you the three attributes that define a waveform and which waveforms are generally known as RF. You'll find out what impedance is and how it affects the performance of RF circuits, and how modulation is used to transport signals via RF and other waveforms. You'll also learn about noise and how it affects signals. Finally, you'll learn about some of the characteristics of RF signal travel in transmission medium. To begin, let's define what we mean by RF theory. RF theory describes signals in a range specified by government agencies as radio frequency. Understanding signal operation in that range involves answering what is for several concepts associated with those signals. Let's begin with signals in general. There are proofs in higher mathematics that show how all signals, irrespective of their shape, are composed of sums of individual sine waves. This basic waveform is therefore the foundation for any explanation of the signal part of RF theory. A sine wave has three basic attributes that can be changed and measured. Amplitude is the height of the sine wave at its peaks. Frequency is how often it repeats per second. Phase is when it begins relative to some reference point. A good example of how these properties play a role in building other waveforms from simple sine waves is a square wave. This waveform can be shown to be the sum of a sine wave at a given frequency and other sine waves at odd multiples of the given frequency. Spectrum is the word that describes a range of frequencies. The U.S. Department of Commerce defines the RF spectrum as the range of frequencies from 3 kHz to 300 GHz. Cable telecommunications sends signals to its subscribers in a continuous subset of the RF frequency spectrum from 54 MHz to 1 GHz. In addition to these downstream frequencies, there is also a set of frequencies dedicated to upstream transmission from subscribers. In the U.S., this band is from 5 to 42 MHz. Impedance is a measure of the restriction of current flow in an alternating current circuit. Resistance is a subset of impedance that applies to circuits where only direct current is flowing. Impedance is calculated as the ratio of the RMS value of a voltage across a circuit element to the RMS current amplitude through that circuit element. RMS stands for root mean square, which is a mathematical procedure to find the average value of the alternating current over time. The formula for impedance is similar to the formula for DC resistance, but unlike DC resistance, impedance is not a constant. Rather, it varies based upon the frequency of the AC signal present at the circuit element and has capacitive, inductive, and resistive components. A formula for calculating impedance shows how engineers improve circuit performance by adjusting the capacitance or inductance of a circuit. You can see from this formula that if the inductive and capacitive components of impedance are equal, they effectively cancel each other out. This is the principle used to improve the frequency response of cable plant, which is the subject of our next slide. Frequency response is the graph of the loss of a system operating across its operating spectrum. In a coaxial cable plant, it is typically measured in dB per 100 feet. The frequency response reflects the changes in impedance due to changes in inductive and capacitive reactance that occur as frequency changes. In a cable system, the frequency response of the system is known as the slope. Coaxial cable systems have a higher impedance as frequency increases. Therefore, the graph of frequency response of an HFC plant shows an uphill signal as frequency increases. The variation in level of signal for different frequencies needed to compensate for slope is called tilt. Equalization is the addition of inductance and capacitance to a circuit to counter the effect of the reactance that causes frequency response. Equalizers are a type of frequency-selective filter that attenuates lower frequencies more than higher ones. Ideally, the frequency response of an equalized circuit will be flat across the range of its operating frequencies. Modulation is the transporting of information in one signal by another signal that has been modified by the content of the first signal. The purpose of modulation is to carry a signal further or more efficiently than the signal could travel by itself in its native form. The graphic on this slide is a good illustration of how this works. In this illustration, think of the word modulation as the signal being used to transport another signal. Now, look at the curve that is formed by the upper and lower boundaries of the letters of the word modulation. In our illustration, this curve is a signal being transported on top of the word. We can see the information in that signal, that is, the shape of the curve, because the normally linear arrangement of the letters of the word modulation has been changed to follow the shape of the curve. In this example, the word modulation has become the carrier of the curve. In modulation, this term, carrier, is used to denote the signal that is being modulated. There are many methods of modulation in use today, both for analog and for digital signals. Basic methods are amplitude modulation, where a signal changes the amplitude of a carrier, frequency modulation, where a signal changes the frequency of a carrier, and phase modulation, where a signal changes the phase of a carrier. For digital signals in particular, these methods are often combined, resulting in quadrature amplitude modulation, or QAM, and quadrature phase shift keying modulation, or QPSK. The details of how each method of modulation works are beyond the scope of this RF theory primer. Signal noise is any unwanted signal on the transmission medium. Two common forms of noise are impulse noise, which are spikes of energy, and continuous noise, which is low amplitude energy that is continually present. Impulse noise typically originates from electrical arcing, such as that which occurs with electrical switch operation or lightning. Continuous noise comes from multiple sources. Some is due to collisions and scattering that occur at the atomic level of conductors, as charges being transported encounter thermally excited electrons in the crystal lattice structure of the conductor. Another source of continuous noise is cosmic background radiation noise, which scientists attribute to the Big Bang that created our universe. Unlike valid signals, impulse and continuous noise are random. Another type of noise that is particularly vexing in cable system upstreams is ingress noise. This noise is electromagnetic interference generated by devices that have an electrical or wireless path to a cable system, typically through power systems or faulty shielding in cable plant. Examples of sources are paths through TV set power supplies and ingress via improperly installed F connectors. The bottom line on noise is that when it is present on a transmission line in any form, it is added to valid signals, resulting in signal distortion. Intermodulation distortion is another form of noise that is the result of a signal being processed by a non-linear system. A non-linear system is one in which signal levels are not processed equally over the entire amplitude range of the signal. For example, an ideal linear amplifier would faithfully reproduce a larger magnitude version of an input signal. But when the amplifier is either under or overdriven at the input, it will apply different amplification to different parts of the signal, or even not allow the signal value to rise above a certain value known as the clipping level. Diode junctions can also produce non-linearities. In RF circuits in particular, the diode junctions may not even be an intended part of the circuit. For example, to an RF signal, a corroded connector may effectively become a diode. When two signals, such as those shown in this frequency diagram at F1 and F2, exist in a non-linear system, they modulate each other, resulting in lower amplitude intermodulated signals at both the sum and difference of the frequencies of the original signals. Intermodulation distortion occurs when one of the intermodulated signals is at the same frequency as a legitimate carrier frequency such as F3. The amplitude of the signal at F3 is the sum of the amplitude of the intermodulated signal generated by the signals at F1 and F2, plus the amplitude of the legitimate signal at F3. The result is distortion of the legitimate signal at F3. Now that we've covered signals, let's take some time to look at how these signals travel in the media used for their transmission. The first concept we will discuss is velocity of propagation. Velocity of propagation is the speed at which electromagnetic signals such as RF travel in a given medium. In the absence of a medium, the velocity of electromagnetic waves is the speed of light in a vacuum, approximately 3 × 10⁸ meters per second. Other media, such as a coaxial cable, have velocities of propagation that are less than the speed of light. This difference is due to wave flow opposing fields established in the dielectric of a coaxial cable as current flows. The ratio of the speed of electromagnetic waves in a dielectric material to the speed of electromagnetic waves in free space is called the velocity factor. The velocity factor for a coaxial cable is the reciprocal of the square root of another coax property called the dielectric constant. Multiplying the speed of light by the velocity factor for the dielectric of a coaxial cable gives the velocity of propagation for the coaxial cable constructed with that dielectric. Skin effect is the property of a conductor that causes current flow to decrease exponentially with depth from the outer surface. The illustration of a coaxial cable in this slide points out that this phenomena holds for both the shield and the center conductor of a length of coax. The distance from the surface to where the current has decreased to about 37% of the surface amount is called the skin depth at that frequency. Skin depth is inversely proportional to the square root of the frequency of the current being transmitted. Over a typical downstream frequency range of 54 to 750 MHz, the skin depth in copper will vary from 3500 thousandths of an inch to 900 thousandths of an inch and will increase to 12 10,000ths of an inch at 5 MHz. Conductive losses are the main source of cable attenuation, and skin depth has a profound effect upon conductance at different frequencies. Skin effect causes the conductor to behave electrically as though it were a tube of material whose thickness is equal to the skin depth, with the current distributed equally throughout its volume. Since skin depth decreases with the square root of frequency, so does the effective size of the conductor. This phenomena contributes to cable system frequency response that was discussed earlier. Skin depth has several implications to cable manufacture and handling. For example, proper tools need to be used to prepare cable for connectorization, since it only takes a nick in the center conductor or shield to very markedly decrease current flow. From a manufacturing standpoint, a cable made with copper cladding over a less expensive core can have the same electrical properties as a solid copper conductor. Reflection is a phenomena caused by mismatches in impedance where a conductor is terminated or where two conductors are joined. At the joint, part of the energy in the signal is transmitted through the interface and part is reflected back toward the source of the signal. The reflected signal adds constructively or destructively to the original signal, depending upon whether the instantaneous polarity of the reflected signal matches or opposes the instantaneous polarity of the original signal. We can directly observe a similar phenomena by looking at how light behaves when it passes through a piece of glass or the surface of a body of water. Due to differing indices of refraction for air and glass or water, part of the light reflects back to its source, creating a reflected, lower-intensity image that appears to be coming from the other side of the surface. Reflection in a conductor has several field implications. For example, when connectors are corroded or improperly installed, there will be an impedance mismatch that will increase reflection and degrade signals to the subscriber. Return loss is a measure of the incident power that is reflected back toward the opposite end of a cable from a termination or other discontinuity in the characteristic impedance of the cable. The formula for return loss is R sub L equals 10 log P sub I divided by P sub R, where P sub I is the power level of the incident signal and P sub R is the power level of the reflected signal. A high return loss indicates that two cables are well matched. To sum up, we've covered sine waves and their characteristics, impedance and how it relates to AC current and voltage, a general model for modulation and a list of some widely implemented forms of modulation, the meaning of noise and its effect, and some of the unique characteristics of RF signal transport in media such as coaxial cable. This section is a primer on cable RF spectrum. The intended audience is a person who has no previous knowledge of radio frequencies and their use. This may include entry-level technicians and several categories of personnel who interact with people that work with electricity, electronics, and electronic equipment. In this primer, we will cover the definition of spectrum and how it relates to sine wave frequencies. You will learn where cable's radio frequency section of the electromagnetic spectrum is located and why that section does not need to belong only to cable. You'll see how individual services are allocated space within the cable spectrum and learn about tools to view signals within a spectrum. You'll also see examples of both analog and digital video signals as viewed by one of those tools. Understanding spectrum starts by understanding sine waves. There are proofs in higher mathematics that show how all signals, irrespective of their shape, are composed of sums of individual sine waves. This basic waveform is the building block of any spectrum. A sine wave has three basic attributes that can be changed and measured. Amplitude is the height of the sine wave at its peaks. Frequency is how often it repeats per second. Phase is when it begins relative to some reference point. Frequency is the attribute that plays a key part in building spectrum. Frequency is measured in units of hertz, which denotes 1 cycle per second. Thousands of hertz are known as kilohertz, and millions of hertz are called megahertz. Spectrum is the word that describes a range of frequencies. The full electromagnetic spectrum spans frequencies ranging from subaudible on the low end to gamma rays on the high end. Until the advent of fiber optics, most traditional communications work had been done in the radio frequency range of the spectrum, which the U.S. Department of Commerce defines as 3 kHz to 300 GHz, and the next higher frequency grouping called microwave. Fiber optics extends the realm of communications to frequencies just below visible light. This primer will focus on the RF spectrum. To avoid conflicts and interference, frequencies within the RF spectrum are managed and assigned by governmental agencies within each country. In the U.S., cable telecommunications has been assigned the RF frequency spectrum from 54 MHz to 1 GHz to send signals to its subscribers. This group of frequencies is called downstream. In addition to these downstream frequencies, there is also a set of frequencies dedicated to upstream transmission from subscribers. In the U.S., this band is from 5 to 42 MHz. Bandwidth is the term used to describe a set of frequencies that fall within a contiguous range. The bandwidth of a cable system is the total range of frequencies that the cable system is capable of transporting. It determines the number of video channels and services that can be offered. It's important to know that while cable has its own RF allocation, many of cable's new services also use other RF frequencies in wireless applications to extend cable plant. In some cases, the reason is to overcome physical obstacles, such as unavailability of right-of-way between two locations. In other cases, these technologies are easy solutions to interconnection of devices within a customer's home or business. Most of the electronic circuitry and physical plant that we use in cable has properties that vary with frequency. Collectively, these effects are known as frequency response. Most of frequency response is due to circuit properties called inductance and capacitance. A more detailed discussion of these topics is included in the Power Theory Primer, but for your understanding of spectrum, it is sufficient to know that capacitance and inductance are common causes of variations in power loss, current flow, and voltage levels that depend on signal frequency. Roll-offs and suck-outs are two common phenomena caused by this frequency sensitivity. A roll-off is a situation where signal strength progressively decreases above or below a certain frequency. Suck-outs are sharp decreases in signal strength at particular ranges within the spectrum. Signal strength on either side of those ranges is markedly higher than at the suck-out. Personnel involved with maintenance of cable plant need to know that there are ways to counter the natural frequency response of a circuit. For example, tilt is a change in signal strength that compensates for increased impedance to current flow. It gets its name from the fact that the change in signal strength, like the circuit's impedance, progressively varies with frequency. Equalization is more complicated, but it involves the use of external capacitance and inductance to counter the effects of inductance and capacitance within an electrical circuit. While a range of the RF spectrum has been assigned to cable by governmental agencies, cable does not totally own that spectrum. Other industries have also been assigned the use of the same range for different purposes. This includes paging, satellite, cellular, and commercial aviation systems. Despite these multiple assignments, signal interference is not a problem when cable plant is properly maintained. This is because each industry uses a separate physical medium to transport its signals. Cable signals are transported over coaxial or fiber optic cable, while these other industries transmit their signals over the air. Problems can occur, however, when there are physical breaks in cable's media, where RF signals can escape or leak into the air. At that point, the cable plant acts like a transmitting antenna, and the leaked signal will interfere with legitimate over-the-air signals. For this reason, cable operators are obligated by federal regulation to avoid leakage, which is also called signal egress. Causes of leakage include faulty or improperly installed fittings, cuts in cable, or improperly shielded subscriber equipment. While a large part of plant prequalification and maintenance is to ensure sources of signal egress are identified and fixed, the best way to avoid leakage in cable plant is to use proper installation procedures and use of cable that minimizes the possibility of faulty connector installation. For example, a common problem with tri-shielded drop cable is difficulty in removing the outer tape and the associated increased possibility of cutting braided shielding, when this is done by hand as a separate step rather than with a cable prep tool. The use of tri-shield drop cable manufactured with the outer shield bonded to the tape eliminates the need to remove the tape as a separate step and avoids inadvertent damage to the braided shielding. FCC Regulation 76.611 specifies cable telecommunications signal leakage performance, and compliance must be filed with the FCC at least once per year. Cable companies prove compliance by documenting the results of system audits. Flyovers and ride-arounds use planes and trucks equipped with RF receivers tuned to cable frequencies and attached to receiving antennas to find parts of the system where signal is being radiated rather than contained in plant. Many cable systems require their technicians to detect and log leakage while performing installations or other field duties. Now that we've identified where cables' frequencies are located in the RF spectrum, let's look at how these frequencies are used. Cable spectrum is divided into channels. Depending upon where you are in the world, these channels are 6 or 8 MHz wide. The U.S. standard is 6 MHz. Individual signals for video, voice, or data are therefore assigned a specific 6 MHz segment of the network's bandwidth. Downstream analog video was the first use for these channels. Frequencies within each 6 MHz segment were designated as carrier frequencies for separate components of a complete video signal. The details of how these frequencies carry information is the subject of another primer on modulation. Without getting into the details, however, it is possible to point out that an analog video signal requires 3 separate carrier frequencies within a 6 MHz band to transport its video motion, audio, and color information. The cable telecom industry is rapidly migrating away from analog technology to digital. Like their analog counterparts, digital signals are assigned 6 MHz channels within cable spectrum. However, they use a different form of modulation and therefore look quite different than analog signals. Unlike analog, digital signal information is distributed across the entire channel, rather than being contained in carrier frequencies. For technicians, this means that digital troubleshooting is done differently than analog troubleshooting. New types of test equipment, which will be discussed later, are required to determine whether signals fall within prescribed limits. Efficient use of cable spectrum depends upon a well-defined system for channel allocation. As we pointed out earlier, cable's downstream spectrum ranges from 54 MHz to 1 GHz. Channel 2 is 54 to 60 MHz. Channel 3 is 60 to 66 MHz. And Channel 4 is 66 to 72 MHz. This allocation continues for analog video across the spectrum to 550 MHz and is the assignment for analog services. In systems upgraded from 550 MHz to 750 MHz, digital services are usually added to the new bands. This continues with 860 MHz and 1 GHz systems. It's important to note that cable channel assignment can and does vary between cable systems and even between serving areas in a cable company. This is possible because the signals in each cable system are contained within the media of that system's distribution plant. Unlike over-the-air broadcast, there is no possibility of interference between adjacent cable company systems. In addition to downstream frequencies, there is a set of frequencies dedicated to upstream transmission from subscribers. In the U.S., this band is from 5 to 42 MHz and is divided into 6 MHz channels. One of the most apparent differences between downstream and upstream channel assignments is that there is only space for 6 upstream channels, which is a fraction of the downstream channel capacity. History is the reason for this difference. Cable's first product was one-way video television. With this product, the only information that was required back from the subscriber was simple control and maintenance messages. In this environment, the 6 upstream channels could easily be shared by all services. As new services were added, more need emerged for upstream communication. Data, voice, and most recently interactive television are increasingly requiring symmetrical upstream and downstream channel capacity. Even with channel sharing between users and applications, this places tremendous demands upon upstream channel usage. In both upstream and downstream directions, continual addition of new services has resulted in fully allocated spectrum assignments. Although digital services permit multiple users to share a spectrum channel, high usage of these services means that channels are continually carrying information. In order for systems to operate without interference that causes service degradation, the signals in each channel need to meet strict requirements. Technicians need to be skilled in understanding, measuring, and meeting several specifications, including traditional proof-of-performance criteria and newer DOCSIS parameters. Although simple meters can be used for some of these measurements, most technicians will also need to become familiar with the operation of a spectrum analyzer, to view signals across a range of frequencies. The main components of a spectrum analyzer are an RF receiver and a visual output that displays a signal's amplitude and frequency components. The RF receiver continually tunes across a selected band of frequencies, so the display is the spectrum within that band. The number of controls and display options vary with the models and manufacturers of spectrum analyzers. Some, such as the one illustrated here, include the capability to simultaneously display multiple stored images that allow a technician to compare and contrast signals. For digital signals, a QAM analyzer supplements information from a spectrum analyzer. QAM analyzer displays are often called constellation diagrams because they look like clusters of stars. Each of the stars, however, represents the instantaneous phase and amplitude of a modulated digital carrier. The fuzziness of the stars and the shape of the overall constellation provide information on signal parameters that can be used to troubleshoot and adjust system performance. Digital analyzers add qualitative information to the visual constellation display, such as bit error rates and noise levels. The specific types of information and their use in troubleshooting is beyond the scope of this primer, but you need to be aware that these aids are increasingly becoming a necessary part of your toolkit. Before closing this topic, it's reassuring to note that engineers and planners are working on ways to alleviate some of the problems caused by proliferation of new services and limited spectrum availability. Because cable's distribution plant keeps signals contained within the media used for transport, it's possible to physically split sections of cable plant and use the same spectrum for different purposes in each section of plant. This usually occurs at a fiber node, which is the point where the media changes from fiber to coax. When the node is split to accommodate new plant construction, it's also possible to build out the new leg with fiber to the home that is compatible with existing HFC plant. The move to digital signals also helps. The efficiency of digital modulation and compression permits a 6 MHz band to be used by several separate digital video channels, up to 12 in some cases. Finally, there are ongoing discussions about reallocating downstream and upstream channel assignments such that a more equal split between upstream and downstream will occur. This solution has many field implications, however, including the need to replace all amplifiers and other electronics that separates upstream from downstream. To sum up, we've covered the definition of spectrum as a set of adjacent frequencies, where cable's frequencies lie in the electromagnetic spectrum, how services are assigned parts of the cable spectrum, the importance of avoiding signal leakage, and some test tools used to monitor and troubleshoot spectrum. That completes the Technology Primer module. Thank you.